Hello everyone, welcome to Chem 1429, it's Fundamentals of Chemistry. So today we're just going to cover the material for Chapter 1. And so Chapter 1 starts off by classifying different materials, different matters, and essentially matter falls into three different states, which are basically solids, liquids, and gases. And this stuff can be found in this textbook, so hopefully by now everyone's got this book. And if you read through Chapter 1, you'll see this. I'm not going to go into too much detail here because it's pretty self-explanatory. Then we cover materials that are basically pure substances, or are mixtures. Okay, so pure substances could be elements or compounds, and mixtures, as the name suggests, are mixtures of elements and or compounds. Okay, so essentially we have a pure substance, like say water. Hopefully some of you know that water has a chemical structure of H2O, which is 2 hydrogens for every oxygen. This is actually a compound, because a compound is one or more elements put together, and the hydrogen is actually the element, and oxygen is the element. So H2O is a compound, because it is a combination of elements, hydrogen and oxygen. So it's a combination of those elements. So hydrogen being an element, oxygen being an element. So elements are basic building blocks. So if you have a look on the front cover of your textbook, you'll have this periodic table. So if you just look on the inside front cover, we have this periodic table. And so this lists all the different elements that we have. Now, compounds made from one or more of these elements being put together. Okay. And so if you had a pure mixture of, say, water, for instance, then it's just a pure substance. Again, I'm not going to go into too much detail with these things, because if you look through the book, it's pretty easy. So we have a look at the metric system. So on pages 9 and 10, you want to have a look at the metric system. I think most of you should be pretty familiar with it, but you want to know things like the term kilo means 1,000, so if it's kilometer, it's 1,000 meters. Milli means 1,000th. There's a table on page 10 that will show you this. Centi means 100th. Things like that you should be familiar with, and you'll have to answer those test or assignment questions with some sort of basic knowledge of what those are. And for measuring mass, we use grams instead of ounces and things like that. But the real thing I wanted to cover today is this idea of significant figures. And this is where students can have a lot of trouble when they come to science disciplines. Often students aren't sure why we actually need to use significant figures and things like that. So let's have a quick look. So if we have a number, say for instance like this, 3.08, that is 3 significant figures. Okay. If we get this 1, 2, 3. If you had 4.1, that is 2 significant figures. Now, where it gets a bit more interesting is, say if it was 4.10, that's 3 significant figures. This is because zeros to the right count as significant. When a decimal is involved. Okay, so in this case we have a decimal place, and so zeros to the right are going to count. Zeros to the left don't count. So if we have 0.00021, for instance, that is only 2 significant figures. So 2 significant figures, because zeros to the left don't count. It's only zeros to the right. Also, if we have, say, 820, now you might say, well, that's 3 sig figs because you've got zeros to the right, but there's no decimal place involved. So this is only 2 sig figs as well. And the reason this is because in common day usage, often people will drop the last place when they're not very accurate with it. For instance, say if you bought a loaf of bread that said 820 grams of bread. Now, if you put it on a pretty accurate scale, it wouldn't weigh exactly 820. It might be 818, 822, something like that, but it wouldn't be exactly 820. And so it's implied that if it ends with a 0, it's really only accurate to the 2 sig figs. If it was accurate to 3 sig figs, like for instance, if it did, it was intended that it was accurate to 820 grams and to that last place value, what people do is they put a decimal place there. And so that would then be 3 sig figs. Okay. The basic rule is that zeros to the right count as significant when a decimal is involved. Otherwise, you can't rely on them. Okay, so that brings us to some simple rounding. And the basic rule is that the number that you're rounding, if the number to its immediate right is 5 or greater, you round up. If it's 4 or less, you round down. So let's have an example. So say 21.5 rounded to 2 sig figs. Okay, if we round that to 2 sig figs, equals 22. Because this is a 5, it's going to be rounded up. Okay, if we had 89.373, okay, rounded to 3 sig figs, we'd have 89.4, because the number that I'm rounding, which is that's the first significant figure, second and third significant figure, that third significant figure, the number to its immediate right is greater than 5 or greater, and so this one is going to be rounded up. Okay. If you have a number such as 72.11 and you want to round to 2 sig figs, then this would just become 72, because the number to the right of the second sig fig is less than 5. So I think that's pretty straightforward with the rounding the numbers. Let's have a look at how we add and subtract with significant figures. So first of all, let's do adding and subtracting, which is actually the more difficult to understand. For instance, let's say we have a big pile of dirt, okay, and we weigh that to the nearest kilogram, and that might be 102 kilograms. And then we add to that this very small pebble or something, and it might be measured very accurately to say 1.119 kilograms. If you put that in the calculator, you're going to get 102 plus 1.119 equals 103.119 kilograms. And students would be comfortable with that and leave it like that. But it wouldn't be completely accurate, because with this first larger pile of dirt, the scales mightn't go to any more accurate than 1 kilogram increments. So we're only confident that it's going to be 102 kilograms. And so in actuality, if we did have more accurate scales, we might weigh this and see that it's actually 102.7, or sorry, 102.17, okay, or something. And so there's going to be some extra little bit after it, or there could be a bit less. It might be 101.8, and so that will affect what this number would be. If it was a little bit less than 102, this would be a bit less. If it was a little bit more than 102, this would be a little bit more. So we're not really confident down to the third decimal place here. We're really only confident to this place value. And so when we add or subtract, we have to report the answer to the least accurate place value. Okay, so report answer to least accurate place value. Okay, so in this case, the ones column, so this would be the hundreds column, the tens column, the ones. If we had a look at this, we'd have the ones, the tenths, the hundredths, the thousandths place value. And so we're only confident to the ones on this one. We're more accurate here, but we can only report the answer to the least accurate quantity. And so we must report this answer as 103, and you use a rounding or whatever here, and that would be the more accurate way, or the accepted way that we'd report that. Okay, so let's do another quick example. If we just have a simple case of 22.15 plus 19.1492, if I put that in the calculator, I get 41.2992, but I'd actually report that answer, and you wait till right at the end when you're going to report the answer. If you've got several steps of working, don't round off at this stage. Only round off at the end when all the working's complete. So this would actually be reported to only this place value, because here we're going to the tenths, the hundredths. This one goes to the tenths, hundredths, thousandths, 10,000ths. But we're only accurate here to the hundredths, so that's the least accurate one. It's the same as a chain is only as strong as its weakest link. And so our weakest link here is this accuracy of the hundredths column. And so I'd actually report this answer to 41.229, but now that 9 is going to round this up, and it's going to round that, and so it's really going to be 41.30. Okay. This is for addition and subtraction. And as I gave the example with the piles of dirt, you could see why that's important. When we have multiplication and division, it's much easier in a sense, because all you have to do is count the significant figures. You don't have to worry about the place values. And the reason is because when you multiply numbers, each of those numbers goes through and is multiplying each of those columns. For instance, say if you have 3.2 times 4.7, it would be just like the 3 is going to go through and multiply everything, and then the 0.2 is going to multiply everything, and it's not a case of having to line up the place values like we do in addition and subtraction. If you can remember from perhaps elementary school or wherever you learned to add, that you'd have these one on top and you had to write it so that everything was in the same columns and stuff. With multiplication, it wasn't important. And so here, if we look at that answer, we get 15.04. This would actually be 15, because what you do is you report the answer to the least accurate number of sig figs. Okay, so in this case they're both 2 sig figs, so the answer would be 2 sig figs. If you had say 9.2 times 101.325, that would be 932.19, but we would report that to 2 sig figs. Okay, so that would actually be 930. Again, this 0 is to the right and doesn't count because there's no decimal point there. Okay, so I hope that makes sense. So this is really 2 sig figs. Okay, so that's some help with the significant figures. Next we have to look at scientific notation. So scientific notation really does away with some of the ambiguity you have with those numbers that we just saw that have a 0 without a decimal place, such as the 930 and the 820 or whatever it was we looked at before. And what we do with scientific notation, it's probably easiest just to do an example. So if I had, say, 1047, so I'd write 1047 using scientific notation. You always start off with the first number, which is a 1 in this case, and then a decimal place. Then you write out the rest of the number. Okay. So all I've really done is I've just put a decimal place there, I guess. And then this will be by 10 to the, and you've got to count how how many you've had to move it over. And so if I went back to where the decimal place was, there's really a decimal place there, although it's not written, and so I would have had to have moved it over 1, 2, 3 times. So it would be 10 to the 3. So again, it would have been there, so it would have gone 1, 2, 3, and so this 10 cubed is really 1,000 anyway. So it's just the same as 1.047 times 1,000. That's the way to do it. So let's have a look at a few more examples. So say 47.28 would actually be 4.728 by 10 to the, I've had to move it over 1, by 10 to the 1. Okay. You could also just leave this by 10 instead of having to do the 1. If we have, say, 862.0, that will actually be 8.620 times 10 to the 2. And so we have to make sure we put the 0 there, because this is significant in this case. It's to the right and there's a decimal place. So this 0 is actually significant. So I must include it in my scientific notation. Okay. You can also deal with smaller numbers. Okay, if I want to write that as scientific notation, again, I just start with the first one, 2.171, and this number is significant, this 0. Okay, but then I have to look at how many many places I had to move that decimal point. So that'd be 1, 2, 3. So it's times 10, but instead of the positive 3, it's by 10 to the minus 3, because I've had to go in the opposite direction. The book sort of gives a few examples of this, and it's worth reading through those examples to make sure you're familiar with that. But generally, it's not too hard. So we can go the other way. We might start off with a number like this. Okay, if you wanted to go back the other way, where we were converting it into what it would be like, it would actually be like this. Okay, and that's because if you look at it, I'd have to go 1, 2, 3, 4, 5 to go back to this way. Okay, so generally a little trick is that if it's by 10 to the minus 5, I'd have to have 0.4 zeros in a row. Okay, because that's what's required. So it's usually one less. So if it was, say, 2.32 by 10 to the minus 6, for instance, then I'd know I'd have 0.1, 2, 3, 4, 5. Okay, to get to the right place value. So these are just going backwards. I hope that sort of makes sense. Sorry. So I hope that sort of makes sense. Why that's necessary, because it's really a total of 6 zeros. It's 1, 2, 3, 4, 5, 6. There's 5 after the decimal point, and there's this extra 1 to get us back to where we were over here. Okay. If you have problems with this, please email me or give me a phone call, and we can talk about it. I'll also be in my office a lot of the time during the summer, and so I'm more than happy to help with those things. Let's move on and have a bit of a look at converting things. So a lot of your first assignment will be about converting different quantities, and so let's look at some of those. So maybe I might say let's convert 35 miles per hour to meters per second. Okay, so if I was going to do that, what you need is some conversion factors, and so we'd have to know that in the back of your book. So in the back of your book you will find different conversions, but aside from that, you could just Google them and they'll often come up quite easily. But just using the back of the book, we'd have, here we are, 1 kilometre equals 0.621 miles. In the back of the book we also have, well, you should know that there is really 1,000 meters in 1 kilometre, and you should know that 60 seconds equals 1 minute, 60 minutes equals and 1 hour. Okay, these are the things that we need to do this question. And this is how we start off. So I have 35 miles per hour. Then what I do is I draw a box for the first conversion. This is just a fraction. And so I want to use a conversion factor that's going to get rid of the miles. And so up here I see that we can convert miles and kilometers together. And so I'm going to put the 0.621 miles on the bottom here. Everything says miles, MI, and the 1 kilometer on the top. This is because the miles will actually cancel. Okay, just by doing this simple step, I've now got the units in kilometers per hour. Okay, still that's not complete, so we need to convert our kilometers to meters, because the question was asking just to convert meters per second. So I go back up here and I know there's 1,000 meters in 1 kilometer. So where am I going to put the kilometer term? It's got to be on the bottom again so that I can cancel the kilometer. So 1 kilometer equals 1,000 meters. Okay, so now I'm going to be in meters per hour. They're the units left. Now, but I want meters per second, so I'm going to have to convert the hour. So I want to get rid of hours. So I know, look up here, 1 hour is 60 minutes. Okay, so 1 hour is 60 minutes. And again, I'll put the hour on top here so that it's going to cancel with this one on the bottom. So now I'm in meters per minute, and I want the meters per second. So the final conversion is going to be converting the minutes into seconds. And so I look up here and I know there's 60 minutes in, there's 60 seconds in 1 minute. So I put the 1 minute on the top and the 60 seconds on the bottom. Okay, so that's going to cancel. And so all up, you multiply in your calculator everything that's on the top. And so I start off with 35 times 1,000. That's, you don't ever put in the ones, equals, and then I'll divide it by 0.621, and then I will divide it by 60 divided by 60. Okay, and so that will give me 15.656 meters per second. But this isn't the right significant figures. All in here we've used multiplication and division, and so I've got to report my answer to the correct number of sig figs, which is 2. Okay, so this is going to be actually 16 meters per second. Okay, just a word on exact numbers. Sometimes you have exact numbers. So for instance, if I wrote down if I said to someone that I have 3 apples, you would know that I have exactly 3 apples, not 3.2 or something like that, because it's an exact number. It's sort of given for what it is. And but if someone said they had 3 kilograms of apples, well, that's probably not an exact number. It would be unlikely that they would have weighed it out. There's no real precision in that 3 kilograms of apples. That could be 3.1, 3.05, 2.98, something. We don't know exactly. And so this one here is known as an exact quantity, but this one's an inexact because it's not exactly right. And so just use, the reason I'm emphasizing this is just in that last example where we had 1 minute equals 60 seconds. This is an exact quantity, this 1. It's not it's not 1.07 minutes is 60 seconds. It's an exact quantity. So you don't worry about counting that towards your significant figures in the previous example. Okay, it's the same here with the, I'll just go back to that previous example, with the 1,000 meters. We know by definition that there's 1,000 meters is 1 kilometer. So I don't look at the 1,000 and say, well, that's really one significant figure because there's zeros to the right without a decimal place. It's by definition, the kilometer means 1,000 meters. Okay, so there's exact numbers. So don't consider the exact numbers when you're looking at significant figures. But at any rate, I think we should do another example on conversions because students often struggle quite a lot with them. So let's try and convert, say, 55 pounds to kilograms. Okay, and so you need the conversion that one pound equals 0.454 kilograms. So this one's quite easy. We have 55 pounds, and again, draw your boxes. Now there's nothing on the bottom in this case, but you can still consider just being 1 on the bottom or something. There's no units on the bottom in this case, but it's still worth drawing the boxes. At least that's the way I like to do it. And so then we need to use this conversion here. And so which one are we going to put on the bottom? Well, we want to cross off the pounds. So I'm going to put the 1 pound on the bottom. And I'll put the 0.454 kilograms on the top. And the pounds obviously cancel. And so this answer is 24.97 kilograms. So that's a simple way to do conversions. Again, a lot of students sort of struggle with it, but it doesn't necessarily have to be that difficult. So moving along with some of chapter 1, we also have to consider density. And again, make sure you're in the right units. So density is given by D equals M over V. So that term there is our density. That's the mass, and that's the volume. So density equals mass over volume. So an example would be what is the density of a steel ball that has a volume of 2 mils, so 2 milliliters, and a mass of let's say 41.0 grams. So to answer the question would be density equals mass over volume equals 41.0 grams over 2 mils equals 20.5, is that right? 20.5 grams per mil. That's the right significant figures because this quantity here is 3 significant figures and this quantity here is 3 significant figures, and so we're all okay to have this one as 3 significant figures. Okay, so the units in this case are grams per mil, but you've got to be careful in the question and look at the answers. If it's reporting answers in grams per mil, but in the question you're given litres. You'll have to convert the millilitres to litres first. Same with mass. If the answer is reporting grams per milliliter, but the mass is in the question is given in kilograms, you'll have to convert the kilograms to grams first. And this could be vice versa too. Maybe the answer is reported in kilograms per mil, and you'll have to convert to grams, kilograms, or something like that. So always be careful of your units, and that's where a lot of students tend to trip up with that. And so you should also be proficient in rearranging equations. So if you were given another density question where it said mercury has a density of 13.6 grams per mil, what is the volume of 10.0 grams of mercury? So you'd start off with the original formula, density equals mass over volume, and you have to rearrange this to get volume by itself. And so because you look at what you're given, so you look at your basic formula, you say, are you given density? Yes. Are you given mass? Yes. What don't you know? You don't know the volume. So we have to rearrange this, and so this would be dV equals m, for multiply both sides by v, and then I can multiply both sides, divide both sides by d, and I'd have v equals m over d. Okay, in this case it's going to equal the 10 grams over the 13.6 grams per mil. These grams actually cancel, and then we have 0.7, and we want it to be 3 sig figs, 735 mils. Because this mils is a per mil on the bottom, when it goes up the top it becomes a mil again. Hopefully that makes sense. So you should be able to rearrange equations as well, and if you have a weakness in that area, please come and see me or call me, email me, and we might be able to work through some examples together and hopefully get through it. Just one other thing that you'll be tested on is regarding Fahrenheit. There's an equation that relates Fahrenheit. So the temperature in degrees C is equal to it's equal to 5/9 of the temperature in degrees Fahrenheit take away 32. Okay, so you can verify that formula. And so for those of you that aren't really familiar with the degrees Celsius scale, it's basically scaled such that water freezes at 0 and boils at 100 degrees Celsius. So you can verify that. So e.g., what is 212 Fahrenheit, or degrees Fahrenheit, in degrees C? Okay, and so you know that water boils 212, and we'd have temperature in degrees C equals 5/9 of, in this example, 212, take away 32, equals 5/9 of 180, and that is going to give us our 100 degrees Celsius. Okay, so that'll be a question that you'll be asked about. And so you want to sort of know this formula, and the book perhaps gives it a slightly different form. Instead of having 5/9, the book uses 1.8. Well, uses 1.8 instead of 9/5, I should say. But that's on page 24. The equation is slightly rearranged. The other thing we have to deal with is this concept of absolute zero and Kelvin. Okay, so just a bit of background on that. It surprised me when I was first studying chemistry that there is this concept of absolute zero. I just never really thought about it, and I thought that you could just keep going colder and colder and colder and colder. But it turns out that there is a minimum temperature you can get to, and that's minus 273.15 degrees Celsius. So I'm not sure what that is in Fahrenheit. So absolute zero is minus or negative 273.15 degrees Celsius. You can't go any colder than that. So from this, they decided to make the Kelvin scale. So you start from zero and go up in the same increments as degrees Celsius. So, like I just said before, with degrees Celsius, you look at zero being the point that water freezes. Well, with the Kelvin scale, you look at zero being absolute zero, and so, but then you go up in increments, the same step gap, if you like, when you measure temperature as what degrees is. So the Kelvin, so the temperature in Kelvin equals the temperature in degrees C plus 273.15. So for example, what is 100 degrees C in Kelvin? Might make it a decimal point there so we go to 3 sig figs. What is 100 degrees C in Kelvin? And the answer is temperature in Kelvin equals 100 degrees C plus 273.15 equals 373.15 Kelvin. Okay, so this is pretty easy. I'll leave it there for examples. If you have questions, just look through the book. This is on page 24 again, and it shouldn't be too hard. The book also mentions this idea of specific gravity. I'm not sure that I'll test you on this, but it's just in case I do, I guess. So worth knowing. So specific gravity equals density over density of H2O. So this would be like the density of object. That's probably right. Density of object over density of water. Now the thing to know is that the density of water equals 1.00 grams per mil, at least at 4 degrees Celsius it does. And so the density of water is 1.00 grams per mil. Okay, so if we use that mercury example, what is the specific gravity of mercury, which has a density of 13.6 grams per mil? Well, the answer is easily that it's going to be 13.6 divided by 1, which is just 13.6. So it's 13.6. But we don't have the units, because the units, if this is in grams per mil and this is in grams per mil, the grams per mil are going to cancel. So we'll leave it there for today's lesson. And again, please feel free to contact me and we can discuss any difficulties you're having. Also, there are many good web-based resources, and there's probably a lot of YouTube videos that cover this stuff, and you might be able to learn from those resources better, or things might be clearer than what you're sort of understanding from me. So please feel free to utilize those resources, and often a Google search of them will show up a lot of results. Okay, thank you.